So, ladies and gentlemen, we'd like to welcome you to the Spectradyne webinar that's going to be taking place today. We're honored to have both Jean-Luc Fréquin, who is the CEO, as well as Lou Brown, who's involved in sales and marketing, give excellent presentations today on an important topic that we are all involved in, which is lipid nanoparticles. Every time we go and get a vaccination against COVID-19, and many of us are doing that, you're getting an infusion of these lipid nanoparticles. And I think today's talk is very timely and an excellent deep dive into the technical specifications in this space. In the past, you've probably heard the Spectradyne team speak specifically about extracellular vesicles and viruses. So today, they're going to pivot a little bit and talk about LNPs. So without any further ado, ladies and gentlemen, we'd like to ask the first speaker, Jean-Luc, to kindly share screen, and we get started. Thank you. Welcome, Jean-Luc. Can you unmute? Yes.
Yeah,
welcome.
can you hear me now?
Yes, we can. Thank you.
Can you see my screen okay?
Yes, we can.
Perfect. All right. Thanks very much for everybody for your time for attending the webinar today. I think we have some pretty interesting content. Hopefully you learned something, and we can learn something from you from questions at the end. Thanks and all for organizing such a well-organized event too. It's great. So the topic of the webinar today is drug delivery vehicles at the nanoscale. So we're going to talk about and share some of the insights we've seen from customer visits in the field about the current state of the art and important considerations that you want to think about when you're characterizing your own LNP samples. So our goal for this webinar is to encourage you to think about two things. First, that you should take the size and concentration of your particles and the measurement of those parameters very seriously. And I hope I can convince you that today. Secondly is I want to get you thinking about whether your instrument, your measurement technique is doing a good job and is appropriate for to give you the results that you need. So I will start by reviewing why particle size and concentration are important, especially in the LNP context. Currently, how they're being measured, review a few different techniques and what we've seen in the field. I'll give a brief overview of how Spectradyne's technology works, because it's an important part of that portfolio. And then we'll discuss how you can know and understand if you're working within the proper bounds for the technology that you're using. Then I'll hand off to Lou. Lou will share some stories from the field that we have picked up along the way. Interesting examples that highlight some of the stuff that I talk about in the first half in the real world. And hopefully you find this interesting. So why is size important? So we've got size and concentration. Size directly impacts the safety and efficacy of a nanoparticle-based therapeutic. So in the first way, particle size determines diffusion rates of the particle and the clearance rates in a biological system, right? How quickly they get cleared out of the organism. And those are essentially the bioavailability of the particle and the therapeutic that you're hoping to deliver with the LNPs. And that itself is strongly impacting the drug efficacy. Particle size also determines particle volume, obviously. And if we think about the particle volume differently, that's the volume that's available for containing the payload of the therapeutic that you want to deliver. And so that is essentially the per particle dose of therapeutic that's available to be delivered in each particle. So hopefully this demonstrates, this highlights why the size is so important for accurate size measurements are so important for LNP development. Concentration is often overlooked, surprisingly, but is also a critical parameter. And that's because it's essentially the dose of the therapeutic that's being delivered. we'll talk about why that's so surprising a little bit later, but it's mostly because the measurement techniques that people are using are not measuring the concentration actually. So as Inal mentioned, the COVID vaccines, the two big ones from Pfizer and Moderna, these are all LNP based drug delivery mechanisms, therapeutics. And so knowing the particle concentration in these samples, coupled with the size, is critical for delivering a safe and effective product. So concentration needs to be carefully controlled. So let me wrap these up into a simple demonstration of an experiment that shows how accurate measurements can deliver fast and well-controlled science. So suppose you've developed two nanoparticle-based therapeutics, A and B. You prepare the formulations, and then we want to test them in a test system of some kind. Maybe it is a mouse model or some other living model, or cell culture media, or maybe a molecular assay. And so we apply each of the formulations to separate test systems, and then we measure the outcomes, right? We compare the outcomes. We want to be quantitative. And I don't think there's anybody on the call here today that would let themselves do this experiment without first controlling for the dose of the formulation, A or B, that's being delivered, right? And given the technology to do so, this is a critical part of running a well-controlled experiment and learning effectively at each iteration of development process. So the accurate size and concentration measurements of LNP formulations is really a critical step for good science. So how are people currently doing this? There's cryo-EM, right? This is obviously a gold standard imaging technique. It's cool because you get to see what the particles actually are, and you can learn so much from that. It's also obviously not practical for routine use. There's not a lot of labs that can have their own cryo-EM system in-house. One of the most common technologies we'll be talking a lot about today that we find in the field is dynamic light scattering, or photon correlation spectroscopy. This is an optical measurement technique, and we'll talk about it in detail. It's ensemble averaging, so it's measuring many particles at once and collecting an average behavior, average properties from those. And it does not measure concentration. So this is kind of a surprising example where dynamic light scattering is used a lot in the LNP world for characterizing samples, but it doesn't deliver any kind of dose information. There's a technology you maybe have heard about called nanoparticle tracking analysis. This is another optical technique. It's actually very similar to dynamic light scattering. And I won't spend much time talking about this today, but there's a very strong growing awareness, especially in the extracellular vesicles field, that the sort of fundamental limitations of NTA are peaking. So if you want to learn more about that, come to our website or ask in the questions later. At Spectradyne, we're big fans of non-optical techniques for particle measurement. There's one that's been on the market for about a dozen years now. It's called tunable resistive pulse sensing, or TRPS. This is an electrical method, so it's an approach that we're a fan of. This particular one has a challenging implementation. That brings us to our technology, which is Microfluidic Resistive Pulse Sensing, or MRPS. This is a powerful technology. It's fast, affordable, and easy to use. And let me tell you a little bit about how it works so that we're on the same page for the following discussion. So Spectradyne's NCS1 is this benchtop instrument I'm showing you on the right here. It's a cutting-edge technology, and it delivers absolute concentration and size of particles starting at about 50 nanometers diameter and up to about 10 microns. As I mentioned, it uses electrical detection of particles and sizing, so it's a non-optical technique, which is really important when you couple it with optical techniques that are orthogonal. And it's fast. It delivers results typically in a few minutes. It's relatively easy to adopt. And one of the features that people like a lot is that it's microfluidics enabled, meaning it only takes just a few microliters of your sample for analysis. Let me describe how it works next. So microfluidic resistive pulse sensing counts and sizes particles one by one very quickly. So you don't have to sit around waiting for thousands of particles. It happens very quickly. And it measures the concentration of these particles and their size on a one-by-one basis as directly as you can possibly do, basically. It's based on the gold standard for decades method of the Coulter principle. We've just scaled it down to the nanoscale. And here's how it works. So we flow the sample in a liquid through a constriction, a bottleneck in the fluid flow. And every time a particle goes through this constriction, we get an electrical signal. This is actual data from a single particle being measured that shows two things about the particle. One is how big it is. So the amplitude of this peak says how big the particle is. And we also measure the flow rate, so the transit time of the particle through the constriction, because that tells us the volume of liquid that we've measured as we count particles, right? So every time we measure a particle, we measure how big it is and the volume flow rate of sample through our detector. So that was one particle. This is a longer acquisition measurement showing many particles being detected. And right away in the data here, you can see there are 4 different sizes of particle signals. That comes from 4 different particle sizes in the sample mixed together. And you can see that directly in the count histograms that we make from this plot. But because we know the concentration, because we know the volume of the sample that was being measured, we can convert these counts from just counts in the histogram to actual absolute concentration. And so this is an example of the final output that our software shows you after a few minutes of measurement. And what we're showing here is a plot where on the y-axis, we have particle concentration in particles per mil. It's a function of size. And on the x-axis, we've got particle diameter across here. And so you can see this sample was composed of a mixture of polystyrene beads, 50, 90, 120, and 150 nanometers in diameter. Importantly, we're measuring the concentration over the whole size range over any given size range. So you might not actually be interested in the concentration of this particle population here. You might be more interested from a science perspective on what's going on in between these sizes maybe, or the impurities there, or maybe there's a biological process that causes aggregation. Those are kinds of things that we can measure directly on our technology. And this combination of accurate concentration and size, together with the ease of use, is just not available elsewhere on the market right now. So that gives you a lay of the land for different techniques that are out there. I want to turn now to the second question, which is, is my measurement method actually doing a good job? Another way to ask this question is, how well do I know the limitations of the technology I'm using, and am I operating within those bounds? So for the context of this discussion, what I'd like to do is focus on dynamic light scattering, DLS, because our experience in the field shows that at least 70% of LNP scientists are relying on this for characterization and even quantification of their formulations. And I hope that you will be thinking about this question up top while we discuss that. Okay. So first, let's review, how does dynamic light scattering work? Essentially, you shine a laser onto the particles in a liquid sample. Okay, remember this is a bulk measurement, so the laser is hitting many particles at once. And while you do that, you monitor the scattered light that comes off the particles in the sample. Now, the particles are not standing still; they're not rigid in the liquid. They're diffusing and they're undergoing Brownian motion. And so, as they bounce around with their diffusion, this modulates the scattered light. And so if we monitor the dynamics of that light, then we can infer properties about the Brownian motion, about the particles with some assumptions. And from that, then you can, again, with some assumptions, you can infer the average size of particles in the sample. And that's effectively what this Z average parameter is that gets reported by dynamic light scattering in the results. So this is a very easy measurement. It's nice because you just shine a laser into your sample. You don't have, there's not a lot of sample prep required, things like that. But there is a very strong fundamental limitation to this technology that I'd like to discuss in detail. So physics dictates that as the scattering intensity, so the intensity of the light that's scattered off a given particle scales with the diameter to the 6th power. That's a really, really strong dependence. And so up here in the right, I've shown you, I picked out a few examples. So suppose we normalize to the intensity from a 50 nanometer particle. We'll call that one arbitrary unit of scattering intensity. If we go up twofold to a 100 nanometer particle, that's already scattering 64 times the light intensity as the 50 nanometer particle. And if we go up again to 200 nanometers, this is not a broad size range, but if we go up just to 200 nanometers, now we're scattering 4,000 times as much light from a 200 nanometer particle as a 50 nanometer particle. So effectively what that means for real world samples, which by nature carry a variety of particle sizes in there, is that the large particles in the sample end up strongly biasing the measurement results from dynamic light scattering. And Lou and I are going to show you many examples of that today throughout the talk. So how can I know if I'm using DLS properly, if I'm operating within its fundamental limitations? So the short answer to that is to use orthogonal techniques, such as our technology, for example. Remember, NTA is still essentially light scattering, similar limitations, and cryo-EM is not practical for routine use. So let's compare dynamic light scattering to microfluidic resistive pulse sensing. Let me show you, this is an actual measurement, okay? So this is the output from the dynamic light scattering instrument for a measured sample. And you can see we have a nice distribution. On the y-axis here, it's the normalized intensity. So it's the normalized scattering intensity. We just set the intensity to 1 here. It doesn't matter. As a function of size. Okay, there's a nice peak right about 165 nanometers, and that's the Z average parameter that the DLS instrument returns to us. And so if I'm an LNP scientist and I'm developing a formulation, I'm thinking, hey, this looks pretty good. I've got a distribution that seems to imply I've got a well-controlled size distribution of particles centered around 165 nanometers. I'd kind of like for them to be smaller a little bit so they can diffuse faster in the, in vivo, but this is a good starting point. And I'd be tempted to use this size or this distribution, the scattering intensity distribution, as a metric for my development, right, of my product. I can push it down, maybe push the size down or something. But I'm a careful scientist, and I know how to use DLS. So I looked up in the ASTM standard, and they're very explicit in this document. Actually, it's funny. For DLS, it says it iterates that this is an intensity distribution, is not a particle size distribution. And importantly, surprisingly, they go on to say that conversion of the intensity distribution to a particle size is ill-advised and fraught with danger. It sounds ominous, but let me explain why. So what have we learned from this measurement? Well, we've essentially just learned the Z average and not much more than that. Why is that? You might be tempted to see the scattering intensity distribution and say, oh, look, that's coming from a peak of particles, actually particles in the particle size distribution with a peak at 165 nanometers. And that may be the case, right? And that would be great, obviously. It'd be a nice, well-defined product. I'll point out that it could also be a well-defined distribution at 1/10 of the concentration, right? So reminder, we're not getting any concentration information from this. But it could also come from a much more complicated size distribution, such as this one. So what I'm showing you here is an example, made up size distribution. But the point is that larger particles that scatter very strongly are just at a lower concentration than these smaller particles that scatter more weakly at a higher concentration. They kind of cancel each other out and give you an average light scattering intensity in the middle. And the ASTM standard essentially says, going from the scattering intensity distribution to a particle size distribution is an ill-defined problem, right? Because there are multiple particle size distributions that can result in the same Z average measurement from DLS. So in effect, DLS is telling us neither the particle size nor the concentration in this sample. And in order to get to that information, we need an orthogonal measurement technique. So let's go back to this actual measured size distribution and run it on the NCS1 instead. When we do that, we see this which is an actual particle size distribution. Remember, we're measuring the concentration as a function of size. These are both measurements of the exact same sample, which was a mix of polystyrene beads, same as what I showed you before, 50, 90, 120, and 150 nanometers in diameter. They were all mixed together at equal concentrations, roughly 2 × 10⁹ particles per mil. And you can see what's happening is the dynamic light scattering is effectively just picking up the big particles in the sample. It's biased heavily towards the bigger sizes in this sample. And it's not really telling you the true composition of the sample. So conversely, NCS1 is showing you high resolution sizing and absolute concentration over any size range in the measured range. So that was just polystyrene samples. Let's move to something more interesting and work from the other direction. So this time we measured the sample on the NCS1, and what I'm showing you here is the actual LNP size distribution. So the size scale starts around 65 nanometers in this case. We're measuring particles up to 250 nanometers diameter. We've got concentration on the y-axis in absolute units. And you can see, note also it's a log axis here. So we've got 4 orders of magnitude of concentration spanned in this sample, roughly. So what would this sample look like in DLS, do you think? So at the low end of sizing, we've got a very high concentration of weakly scattering small particles, right? And then up here, we've got very strongly scattering large particles, but they're at low concentration. And so maybe there's a sweet spot where there's kind of a balance of, most scattering and medium concentration, So we can actually simulate what the scattering intensity profile would look like for this sample. Remember, this is a real sample measurement here. By convolving the concentration and the diameter to the 6 power dependence, we can calculate what the scattering intensity should be for this sample. And it's remarkable, you see a nice peak around 150 nanometers diameter for this sample. If you measure this on DLS, you probably get this for the Z average in the sample. So it's no wonder, but this is an example that a very complicated size distribution like this, it's a broad power law, essentially size distribution, very commonly is what we see in the field for this kind of material, shows, quite reasonably, for good reason now that we know how DLS works, a peak in the intensity, scattering intensity distribution. It's really tempting to take this Z average and try and infer what the particle size distribution is, but remember it's not reversible because it's not a well-posed problem. Lots of distributions can generate this same scattering intensity profile. So really what we've learned from DLS is just Z average, right? So hopefully I've got you to think about the measurement parameters of operating your measurement technique, right? So let's summarize. So DLS always gives an average particle size. It really doesn't matter what's in the sample. For monodispersed samples, that's great because it shows you actually where the peak in the particle size distribution is probably pretty close to where the scattering intensity peak is. But as soon as you have a polydispersed sample or a sample where you don't know if it's polydispersed or monodispersed, this is not an okay method, actually. And in that case, what you need to do is use orthogonal measurements to actually measure the size and concentration of the particles. So hopefully that was informative and helps you understand the examples that Lou will share with you now in the next part of our webinar.
Okay, I've unmuted myself. Hopefully you can hear me and see me, and let me share my screen.
Great.
Hopefully you are seeing my screen now.
Yes, we are.
Great, awesome. Okay, well, thank you, Jean-Luc, for that overview. That's very helpful. And as Jean-Luc said, I'm going to go through some examples, sort of stories from the field, if you will. One thing I do want to point out, just to be upfront about this, is that some of these samples were actually done at customer sites, but we do have permission to use the data. So we are very respectful of proprietary nature of data. It's been sanitized, so you wouldn't know where it came from or anything like that, but they have allowed us to do it. So let's get into the first case here. And this is lipid nanoparticles. And this again was, this actually was a demo I was on, and I came in, set up the instrument, and I didn't know anything about the samples. And they basically said these are LNPs, and they have 3 slightly different recipes. And they had already measured them on their DLS system there. And the results are shown here. Sample 1 showed a DLSC average of 66.5. Sample 2 showed a DLSC average of 66.8 nanometers. And for some reason, they couldn't measure sample 3. And I don't know why that was, but they couldn't. You also notice the polydispersity index. And I already saw a question about that. We can get to this later, but that's the other number that DLS produces. It's kind of a made-up number that attempts to characterize how polydisperse the sample is. And the smaller the number, the more monodisperse it is. So looking at this particular example, one would lead to the conclusion that although they have the same Z average, that sample 1 is a more monodispersed population than sample 2. That's what that would tell you there. So then they gave me the same samples and had me measure them. So let's take a look at what we got. So here is the results from the NCS1 for samples 1, 2, and 3. The first thing you'll notice is that there are clear differences in these 3 populations, as represented by the arrows here, which are pointing to the peak, which is really the mode of the sample. Okay, and so you can see clearly that the green sample has a lower mode than does the blue and that does the red. You also see a lot of very interesting features inside of the distributions. For instance, in this green sample, you can see that you have a nice peak and then it goes down, and then there's kind of a shoulder here. That potentially could be a dimer peak. We're not sure there. But anyhow, that's significant that it's not a nice, perfect Gaussian distribution. And then in the red sample, for instance, you can see the peak is higher, but there's also a very large population of smaller particles, which are probably debris from whatever the process it was to put these 3 together. Now, to give you a comparison, let me overlay the Z average that they had from the DLS. And remember, they could only measure samples 1 and 2. For some reason, they couldn't measure sample 3. So this is exactly like one of the examples Jean-Luc showed, where you kind of have 2 peaks and the Z average ends up being in the trough as opposed to where the actual peak or mode of the data is. And, again, it showed no difference between samples 1 in the blue and sample 2 in the green. And you can see they are very different here. And for instance, in the blue sample, the upper tail, there's a much higher distribution, there's a much higher concentration of particles, say greater than 100 nanometers, which you don't have in the green. Okay, so let's summarize the overall data here, and we'll do that in this little chart here. So I'm showing the peak diameter in this first column, which is the NCS1 calculated peak diameter. Again, you can see they're very different. We had 60, 74, and 85 nanometers for the peak. And then the Z averages were the same for samples 1 and 2, whereas we're showing that they actually differ by 14 nanometers here. Okay. And you can see the number of particles counted. Again, this goes back to what Jean-Luc was saying, in that the system is very fast. And we've counted over 10,000 particles to come up with these distributions. Last but not least, and very importantly, as Jean-Luc mentioned, is we're also getting the concentration. I want to notice one thing here. This concentration number you're seeing is the concentration from 50 nanometers to 250 nanometers. And the way you get that is you actually integrate under this curve. So let's take the red example. We would integrate underneath this curve all the way out from 50 to 250. And that gives us, since that was sample 3, that gives us this 3.2 times 10 to the 12 particles per ml. Now, you can interrogate this distribution any way you want. So if I wanted to find out more about what the population here under this peak is, I would integrate from this trough here up to the top here, and I'd get a different number because I would eliminate this rise in concentration that appears to not to be part of this population. So the software allows you to integrate over any range of particle sizes to get the concentration. And in this case here, we're doing it over the whole range, but you can, in the software, I can type in values. So I could say, give me the concentration from 50 to 75, or you actually can interactively go in and just define it by using your mouse. It's quite powerful. So let's go on to another example. Case 2 here is the effect of extrusion pore size on liposome size. So it's a little bit different. As probably some of you know, liposomes are typically made through an extrusion process, and they use a pore to extrude it through. So in this particular example, we had 2 formulations that were identical, formulation A and B, but the difference was the formulation A was extruded through a small pore and formulation B was extruded through a large pore. Now, in both of these samples, we also spiked in a 150 nanometer control bead, which you can see in the distribution here. The thing that's really powerful about this is that in the NCS1, you can spike in a control bead. So we know that these beads are NIST traceable as 150 nanometers, and we mix them to be a certain concentration. So if I integrate over the bead area here, I can get the concentration results and show that they agree with how I've actually measured them. How I actually mix them together to get this. And the blue here is showing just the 150 nanometer controls. And so you can see they all agree nicely out here at 150 nanometers, which is very, very, very powerful. And that basically validates an in-process validation of the measurements you're taking on those 2 formulations. So what do we notice here? First thing we notice is that the peaks of these 2 extrusions are roughly the same. There's a small difference. It looks like the formulation B through the larger pore actually is slightly higher in its peak diameter, but it's also lower in overall concentration, and it's also wider in the overall distribution, which means we're going to see more particles in the large size here. And that's represented by the difference here between the red and green lines. So for instance, if I integrated where they cross here, where the red and green lines cross here out to say around here, I would get a higher concentration for the red because it shows that here in the graph. Okay, and it's very easy to interrogate the data that way. So I don't have DLS data for this, but because we know how DLS works, we can sort of predict exactly what would have happened had we used DLS. The first thing is that the Z average for sample B, the larger pore extrusion, would be higher than the one for formulation A. And there's 2 reasons for this. One, there is a slight shift here, but more importantly, as Jean-Luc said, there are more large particles, and what that's going to do is it's going to cause the distribution, the Z average, to be skewed towards the right or towards higher sizes. So we would expect, if we did measure this with DLS, that the Z average for B would be significantly higher than A. The other thing is, since the sample B is a wider distribution, we would expect a higher polydispersity index for sample B. And the last but not least thing is that if you were to measure this with DLS, you cannot use a spike in control because these 150 nanometer beads would scatter so brightly that they would skew the Z average much, much higher to a point where it really was meaningless compared to what the actual liposome size are. Okay, you just can't do that. And again, that's because, well, there's 2 things that are happening there. One is just the fact that they're larger particles skews it. The other is that the scattering is also dependent on the refractive index of the particles, and polystyrene beads have a much larger difference in refractive index than do the liposomes. Okay. Now, so the difference is in the MRPS system, we're getting a much more detailed distribution. We're getting a true particle size distribution, not just a Z average. And you can see subtle differences, such as the fact that this has a lower concentration at the peak diameter than the other one. And you can also use these spike-in controls. And I can't emphasize enough how powerful that is, because that allows you to put into a sample a control that gives you NIST traceable size and concentration, reference concentration. And that ensures, if those come out correctly, which they will, that ensures that the measurement you're looking at for the particles you're interested in is actually NIST traceable in size, and that the concentrations that you're getting are correct. Moving on to the last example, this is again LNPs, and this is in formulation process development, kind of an interesting study. Probably a lot of you out there may have familiarity with the Precision Nanosystems NanoAssembler product. Basically, it's a product that uses microfluidics to do a highly controlled mixture to generate particles such as LNPs, liposomes, or polymeric nanoparticles. Okay. So probably some of you are already familiar with it. Maybe some of you actually already use this product. They're very wonderful products. There were two different instruments that were involved in this experiment. The Spark, what they call the Spark system, is it's a low volume. It's used to do early prototyping work. So it produces very low volumes of LNPs, for instance, but it's kind of quick and dirty, and you can get some results very fast. The next step up is what they call Ignite. It used to be called the benchtop. And that's a larger size instrument that can produce larger quantities of nanoparticle output. And so what they were looking for here is a couple different things. They would use the same recipe, if you will, for producing these LNPs in both the Spark and the Ignite. So they wanted to find out, well, there are differences in these instruments. Does the Spark produce the same size particles as the Ignite, for instance, or are there going to be some differences? And they also wanted to see how repeatable the process was. So basically, you're taking the same LNP recipe and you're doing 3 replicates on the Spark and 3 replicates on the Ignite in order to study this. And they, like everybody else, had first measured these on DLS. So take a look at the results here. And you can see the mean Z average over here for the 3 replicates of the benchtop and the 3 replicates of the Spark. The first thing that jumps out to me is that I look at the 3 replicates of the benchtop and I see good consistency. You can see 92.3, 90.26, 89.2 nanometers. So roughly 90 nanometers, pretty consistently produced, okay? And if you look over at the PDI, the PDIs are pretty reasonable as well. I mean, I always say that it should be below 0.2 to get a reasonable estimate. When you go down to the Spark sample, though, you get a different story. A couple things. First of all, it appears that the Spark produces significantly larger particles than the benchtop does. Second of all, though, is it doesn't appear to be very repeatable. We've got measurements ranging from 117 nanometers to 162 nanometers. That's quite a difference. And you will note over on the final column there, it's got a much higher PDI. And again, I tell people that when you have a PDI greater than 0.2, you should be really cautious of drawing any true conclusions from the data you're getting. So let's look at this a little bit differently, and let's look at the Z averages plotted this way. Okay, so the 3 red dotted lines represent the 3 replicates of the benchtop. The 3 blue dotted lines represent the 3 DLSZ averages of the 3 Spark runs. So now we measured them in the NCS1, and I'm going to show you what's really happening in these samples. Very interesting. So we see the 3 red ones here, very repeatable results. And it looks to me like the Z average is around, let's say, 65 nanometers. I'm just eyeballing it. And then the blue Spark measurements are also relatively repeatable, not quite as repeatable as what we see here. but it seems to be just slightly higher. And I'm going to, again, eyeballing this, I'm going to say that the Z average is maybe around 70 nanometers. Okay. So this is actually quite different than what the DLS said. First of all, the DLS said that the Z average was up about 90 for the spark samples. And that's just plain not true. It's really down here at about 60 nanometers or 55, depending on how you look at it. Okay. And secondly, despite what the DLS said, that the spark samples were significantly larger, they're really not that significantly larger. In fact, they're only about 10% larger in size, and they are relatively repeatable, and certainly not as unrepeatable as what would be implied by the DLS results. So just think about in terms of where we progress. We started with the DLS data, which told us that the spark particles were much larger and less repeatable. What we found out in reality is that the replicates are very similar for both the spark and the benchtop. And we also found out that the spark does have a slightly larger mode, but it also has a longer tail. And that longer tail is what explains these Z averages being A, so large, and B, so different. Because that longer tail, again, this goes back to what Jean-Luc was talking about. The larger particles scatter much brighter than the smaller particles. And it's that sixth order dependence. So because of this longer tail on the spark samples, the Z averages are significantly higher than they are for the benchtop. And because this longer tail, what can happen is a single large particle out here, say at 125 nanometers, can skew the Z average greatly. And so what's happening here is this variability you're seeing is being caused by very few large particles out here at the high end of that distribution. Okay, so the DLS gave us a very different story than what the NCS1 gave us here. And to summarize that, let's just look here. We now know that the nanoassembler gives us very high repeatability on both the benchtop and the spark, okay, which was not apparent from looking at the DLS data. The spark, it does produce slightly larger particles. They're not as large, as different though, as at what DLS implied. And that longer tail is what gave us that misleading information. So overall, the DLS measurements that we had early on were very misleading, particularly for the spark example. And this is caused again by that bias to the very, very large particles. And the NCS1 gives you the real distribution that you can actually see features in and you can measure concentration in. And again, that's the real important point we're trying to drive home, is that the NCS1 gives you both accurate size, and that's a true particle size distribution, not just a Z average, and it gives you concentration information. So with that, I'm going to turn it back over to Jean-Luc and let him wrap up, and we'll be ready for questions.
Thanks, Lou. Good. I see some good questions coming in already in the chat. That's great. Thanks. I guess we'll put those all at the end. So let me just wrap up real quick. I hope we've gotten you to consider two questions about your science. One is size and concentration measurements are really important, and so it's important to measure them accurately. And then also that to ask yourself whether your measurement method is doing a good job or not, right? Whether you're working within the bounds of your measurement technology. So to summarize, accurate size and concentration are critical for good science. It's important to know your measurement techniques and to use orthogonal techniques when you can. We're always a proponent of encouraging users to investigate their samples from different perspectives, because you always learn more that way. So please get in touch with us. There's a lot of information on our website, nanoparticleanalyzer.com. We have a page with applications. It's not just LNPs for us, but many of our customers use the NCS1 to characterize other materials. We've got a products page where you can read about the specs, library full of publications, videos, and applications notes. And we maintain a blog page also where you can find measurements of the COVID vaccines, for example. I will leave you with an invitation to send us one of your samples for free analysis to find out what's in there and to make sense of the data you already have. So thank you very much, and I'd be happy to answer some questions now.
Thank you very much to Jean-Luc and Lou for an excellent set of presentations. Ladies and gentlemen, this is an excellent time to ask questions. We've had a lot of questions come through the Q&A and chat box. So if you would like to ask the questions in real time, what you could do is raise your hand electronically and we'll unmute you. And you can ask the question just like you do at a conference, an on-site conference. So we'll start. The first one, we're going to allow you to talk. So there you are. Dr. Kim, welcome. And please, you can now speak. So you can unmute yourself and you can ask your question in real time. Thank you.
All right, thank you. Can you hear me?
Yes, we can. So if you would state your name and then ask your questions for Jean-Luc and Lou.
Sure. Very nice talk. I'm BJ. I'm a postdoc at the Koch Institute. So I submitted actually 4 questions. Let's see if we can get through them. First was, what's the minimum and maximum concentration you can measure on the machine? And what solvents can be used, organic or aqueous? And then the other 2 questions are, how do you get accurate measurement from 50 nanometers to 1 micron range? Because I'd imagine that your microfluidic system that is big enough to detect the microparticles will be too big to measure nanoscale particles. And also for the particles that are less than 50, smaller than 50 nanometers, do they get just left out or do they get included somewhat as the peak at the minimum? So let's say at the 50 nanometer range.
Those are great questions. Thanks. Nice to meet you, and thanks for attending today. The overall concentration range of our platform from 50 nanometers size to 10 microns diameter spans from 10 to the 4 particles per mil up to about 10 to the 11 particles per mil. So that's the answer to your first question. I'll jump ahead to the third question, which is about different measurement ranges. So in order to span that whole range from 50 nanometers up to 10 microns requires 3 separate cartridge measurements. So we have pores with different sizes, right? Different constrictions with different sizes. And particles that are smaller than the detection limit for a given size, excuse me, just are not measured. They don't generate a measurable signal in the system. So that was 3 questions. And the 4th one is about which solvents are acceptable. And by the way, all this information is on our products page on our website. But the only real requirement, there are 2 requirements for the sample diluent. One is that it be conductive. Okay, so generally that means aqueous solutions with some kind of conducting ions in it. And the second one is that there needs to be some wetting agent in the sample in order to help it get into the cartridge properly. And so most of our users use Tween, and I saw a question come up about that in the chat we can talk about. Or there are a couple of alternatives. There's a poloxamer, also surfactant, and you can just add protein like a BSA, something inert, to your sample also. We have not experimented too much with like organic solvents, but we're always interested in learning more. So if you have a specific question, we've maybe tried it before, or we could try it out. Hopefully that answers your question.
Just wanted to add in one quick comment on what you just said, Jean-Luc. When we do multiple measurements with multiple size cartridges, the software can automatically seam those three together into a single distribution. So that's not something you have to worry about.
Yep, thanks. Good point.
Thank you. So we're going to now unmute Barbara. Barbara, please, if you would kindly unmute your speaker and introduce yourself and ask your question. Welcome.
Yes. Hello. Can you hear me?
Yes, we can.
Hi, Barbara.
Okay. Thank you. Hi, here's Barbara Winchigel from Germany. I'm working at Corollas Munich, and I have a question on how the method itself is limited to particle shape. So is it for spherical particles, or is it also for long nanoparticles like let's say nanotubes or so? Is it limited for that? And of course, also the question: what is the drawback or the limitation of your method? I agree, it's very useful for concentration and size, but what are the disadvantages of using your technique?
Great questions. Thanks, Barbara, and thanks for attending today. The question about shape is a really interesting one. You know, the primary measurement that our technology makes of the particle as it goes through the constriction is to measure the volume of the particle. So to first order, we can't distinguish between particles of different shapes. That said, it's possible to imagine if you had we measure multiple parameters of each event, right? Each particle event. And so it's possible to imagine a longer particle that would maybe be distinguishable from a shorter particle or spherical particle by its transit time, for example. It may take longer to get through the constriction. Something as long as a carbon nanotube, we've tried those before, but you can imagine what a bunch of spaghetti at the nanoconstriction looks like. It doesn't work very well, so I don't recommend that application. In terms of limitations of the technology itself, I think you hit it on the head. It's very good at measuring the size and concentration of particles, but for the time being, we can't tell you what the particle was, but that will change, so stay tuned.
Wanted to jump in and add on that also. As Jean-Luc mentioned, we do actually, our raw measurement is actually particle volume, and that's irrespective of what shape the particle is. That's quite different from optical techniques, because optical techniques have to assume that all particles are spherical. And where that can get you into trouble is I've actually done some work with cylindrical shaped viruses that are about 50 nanometers in diameter, and the length might be close to 200 nanometers. And you can imagine that when you illuminate that with a laser for an optical measurement, either DLS or NTA, you're going to get different answers depending on the orientation of that particle, right? But in our system, when I measured these particular cylindrical viruses, they showed me electron microscope images of the particles themselves. And I was able to say, okay, so if we use the formula for a cylinder, the volume of that particle will be X. And then I back calculated what the diameter of an equivalent sphere is. And I said, those will show up at 100 nanometers. And when I measured them, they showed up right at 100 nanometers. And that really proves that we're measuring the volume, not assuming it's a sphere and making it a sphere.
I'll just add to Louis, I'll give him a plug. He wrote a great blog article that is on our blog page about exactly that measurement. So go have a look.
Okay,
thanks, Barbara.
Thank you very much, Barbara. Next will be Dr. Linz. Dr. Linz, you can unmute, introduce yourself, and ask your question. Thank you.
Hi, Tom.
Hey, guys. How are you guys doing?
Good.
All right. So a question for you about some of the imprecision that we're having on our particle counts. like we'll run the same sample a few times and it can be pretty different results. So I get how the measurement is going to count absolute number of particles. I'm good with that. How does it measure the volume? And is that maybe where our reproducibility issues are coming from? Is just the volume is different from sample to sample?
You mean the measured volume is different from sample to sample?
Well, the measured concentration differs. And if the particle counts are just what floats through the pore, I feel like the only reason why we'd be getting variability is the volume. So like, does the particle counter itself actually measure the volume? Is it measuring time? Like, how do you guys get the denominator for a particles per mil calculation?
That's a good question. So we measure the transit time for each particle, right? And I know this is something that you've been talking to our support team about, right? And we're trying to help you out. So the transit time of the particles is what we use with a calibration factor to calculate the measured volume of the sample that was measured. And then it's pretty straightforward. It's the number of particles on a given size range divided by that measured volume. So it's either, if you're measuring a different concentration, it's either because the number, the flow rate's the same and the number of particles is different, or the number of particles is the same, but the calculated volume is different. And it's going to be sample dependent. So I think maybe we need to work more with you on the sample prep, the method development stuff.
So did I hear you right that you're saying, so does the NCS1 control for the flow rate through the pore?
It accounts for the flow rate through the pore. It's a fixed pressure system. And so, but as the transit time slows down, you can double the viscosity of the sample and it halves the flow rate through the constriction. So it detects, it accounts for differences in flow rates that way. Does that make sense?
Okay, and is that auto spit out in like the data report? Does it take that final volume pushed through into account?
Yep.
Like maybe depending on viscosity?
Yeah, the measured volume is one of the parameters in the metadata of the sample.
Oh, okay. I haven't hacked, I guess, deep enough to see that.
It's in the Excel report, the run report at the end of the measurement that you create every time.
Okay.
That Excel sheet, one pager.
All right, thank you for the response.
Sure, yep. And just to be clear, please keep contacting our support team.
Okay.
We're happy to help. We want you to be successful. So please reach out.
Okay, sounds good. Thank you.
Thank you.
Thank you very much, Dr. Linz. The next question comes from Dr. Obaid. Dr. Obaid, please go ahead and unmute, introduce yourself and ask your question. Thank you very much.
Thank you very much. This is Dr. Muhammad Obaid from Jordan. I just want to elaborate about the results of the nano assembler or the benchtop. We know that since the BDI values when it's be less than 0.2, then the particles would be monodispersed. But here you showed that even with BDI around 0.16 and 0.17, still there is a difference between the results of the DS and the microfluidic system. Can you elaborate more about this difference, even though the BDI was quite small? This is the first question. The second one, what about the sample preparation? Is there a minimum volume for the sample for microfluidic system measurement, and does it have to be diluted or not? Thank you.
Great questions. So to the first question, I think it's clear from the discussion of how the DLS works that there are many different size distributions that can yield the same Z average, right? It's really just telling you some kind of weighted average of all the particles that are scattering detectable light, right? So to me, it's not surprising that there can be significant differences in the distributions that end result, that are indistinguishable by dynamic light scattering. And those samples did have a peak, so maybe the polydispersity index was low as a result. But there's a lot of fishiness about, or like wiggle room in what that number really means and how what it really represents about the sample, right? Again, you can't use it to convert to a real particle size distribution because it's not a well-posed problem, right? Even if the number is low. So hopefully that answers your first question. Second question, the sample prep requirements are essentially to make sure the concentration is in a measurable range. So the dilution of the sample needs to be such that you're not counting too many particles, that the particle events aren't overlapping in time, and not so low that you have to wait forever to count a significant number of particles. So that's how we determine the range of sizes or range of concentrations for each of our cartridge sizes. The last question I had it, but I forgot now. Lou, do you remember?
Volume of them.
Oh, the volume, yeah.
Of the sample.
Thanks. Yeah, so the minimum volume of sample to be required at the final measured concentration is just 3 microliters. So
okay.
Dr. Sultana is on the line. I saw her. She has used the NCS1 to measure tick saliva. So you can imagine how small volume that is.
Okay, thank you very much.
Thanks for attending, Dr. Obaid.
The next questions come from Dr. Lopez. Dr. Lopez, please kindly unmute, introduce yourself, and ask the question. Thank you.
Hi, very nice presentation. I think you have a very nice product too. And my question is, eventually we're going to have this equipment to use. I would like to ask you, what mitigation strategies do you propose for this, I would say, issue or problem that you cannot measure below 50 nanometers? Because sometimes, I mean, you could produce lipid nanoparticles that are around that range, and maybe some subpopulation might be lost in the count. What mitigation strategies do you propose for this problem?
Well, so the fact is the limit of detection is 50 nanometers, and so we can't detect particles below that right now. I can tell you that we have done research measurements that have shown particle detection down to 35 nanometers. So it's the direction we want to move. But as you can imagine, it's a challenge to make pores that are small enough to detect those. I do think it's feasible, but it's just not commercially available right now. Does that answer your question?
Yes,
Okay.
And then the other question that I have is, what are the ranges of the microfluidic devices that you use for measuring? Because you mentioned that you have like this wide range from 50 nanometers to 10 micrometers. What are the ranges of these cartridges? For example, if I'm measuring something that is between 50 and 500 nanometers, do I need 2 cartridges, or it could be done with 1?
Good question. So if you go to our website, we have a cartridge map that shows the different cartridge sizes that we have available, the size ranges that they measure, and the concentration ranges that they measure. So I'd encourage you to go check that out. Typically, what people end up doing is settling on one particular size that gives them the regular information that they need about their sample. Once in a while, they'll do a very broad range measurement, but typically in day-to-day use, they're focusing on one size or another. So it really depends on the size range of interest. I think we have 5 different cartridge sizes that are commercially available, and they overlap. So it really just depends on your application and region of interest.
All right. And then the final question is about the operating cost of the device, because you have to buy a cartridge per sample. So what would be the range? Let's say that I have 20 samples to measure, the operation cost other than the equipment cost.
Yep, good question. So cartridges are $9 each. And typically our customers love them because you use one, you run the measurement, and while the one is running, you're prepping the next one, and you don't have to do any cleaning of the instrument in between. So that's cartridges. And then there's really no other operating costs of the instrument. We don't sell any proprietary buffers or anything to use with the instrument. It's just PBS and tween. There's a running buffer that you have to prepare and filter yourself. So it's not a whole lot of other extra costs.
Sounds great. Thank you very much.
Thank you. Thanks for attending today.
I wanted to just jump in on Dr. Lopez's first question and just elaborate a little bit, because I saw one of the other questions that was along the same lines, and basically it's what happens with particles that are below that limit of detection. And the quick answer is, if you remember Jean-Luc's slide, which showed the graph of the particle coming in and the change in voltage, et cetera, there is a background noise level that's always there from the electronics. And so what happens is that when the particle volume goes below a certain percentage of the size of the nanoconstriction itself, the signal produced by that particle, there's still a signal produced, but it no longer rises above the background noise, which means we can't tell you whether that's noise or a particle. And so the signal processing engine built into this automatically cuts off the particles that are smaller. And they don't affect the measurement of the other particles. They pass through, they just pass through undetected.
Thank you.
Thank you.
Ladies and gentlemen, if you'd like to ask further questions, you're welcome to raise your hand and we'll unmute you. In the interim, there's a number of questions that have come in the Q&A box, and I would kindly ask Jean-Luc and Lou to perhaps go through the ones that they'd like to answer right now with the audience, and then follow up individually for those that can be taken offline. So perhaps Jean-Luc and Lou, if you want to read out the question and then perhaps pose an answer to them. Thank you.
Yep, sure. So first one was from Arnab Rudra. I understand that we have to use tween, but what if the LNP is not compatible with tween for some reason, or how do we know if tween is not affecting the LNP? That's a good question. The surfactants that we have tested so far include tween, but also this a poloxamer tool, and we can give specifics for that. It's another non-ionic surfactant. And if either of those are too much of a concern, it is possible to use some inert protein like BSA, for example, as a diluent that serves as a wetting agent. There are papers we can send you that talk about how tween is safe for EVs at least, and things like that. But it's up to you to feel comfortable, obviously. What I would suggest to know whether it's affecting the LNPs or not is to do the measurements and try and detect differences in the size distribution with different surfactants. And that's something that our technology would be very good at answering for you. Hopefully that answers your question. There's a question from Ximin Chen. What are common diluents used for sample dilution? Most people use PBS with tween in it as a wetting agent. That's by far the most common and the most well-characterized sample. As I mentioned, you can use other wetting agents. Most people use PBS because it's compatible with their biological samples. Then Jenny Yang has asked, why does LNP sample profile seem to follow the Gaussian distribution, while other samples such as exosome samples show power law distribution with no peak appearing? There's a second part. Let me answer the first part first. That is a great question for you guys to answer as scientists and researchers of these particles. My understanding is that EVs take a broad particle size distribution because of the diverse origin stories of different biological particles in a complex system. But that's the extent of my understanding of it. So I would encourage you to pursue that topic. It sounds interesting. Second one is how to compare two sample sizes when there's no mean size for each sample. And that is a really good question, because it's really easy with dynamic light scattering to compare two samples, because you get a Z average for each measurement, and they might be different, right? I think the important question to ask is what's that really telling you about the differences between the actual samples? And with our technology, it's important to remember that the data that we're giving back is a much richer data set. It's not just a number, it's a whole size distribution. So it's a number at every size in the measured size range. And so really what we encourage our users to do is do a mind shift where instead of trying to compare just a single number, move into a distribution comparison mindset where you're looking at the concentration over a given size range. And that's where the power of our technology really shines, I think.
Yeah, just to chime in on an example of that, I've seen samples where two samples they're both a power law distribution, as you say, Jenny, and good to hear from you. And what's more interesting, though, is that when you overlay the two samples, what you find is that one sample has a larger amount of large particles and it drops off quickly, whereas the other sample starts with a lower amount of small particles, but then it goes out longer. And they might even have the same Z average if you did a DLS analysis. But the key thing there is that you're seeing that one sample has predominantly more small particles, say below 100 nanometers, whereas the other one has more particles predominantly above 100 nanometers. And that's going to make a huge difference, particularly when you talk about bioavailability and, the clearance rates and things like that. Where in the body can these particles travel to? The size is really important. So one of those samples, because it's got smaller particles, might end up in a different place or concentrating on a different place in the body than the other one because of that size difference. So as Jean-Luc said, it's truly the overall distribution that is important here, and being able to compare the shape and of the distributions is very valuable.
Maybe one last question here from Gitika Raizada. What happens when the size range of our sample is very large? So as we mentioned earlier, it takes multiple measurements to measure that full size range, right? On cartridges that have different aperture sizes. But most people in typical usage end up focusing on one cartridge size that gets them the information that they need. So it's not like every time you walk up to the instrument, you have to do multiple measurements. Usually you focus in on a useful range for what you're working on. Hopefully that happens.
Another part to that question, which it's implied to me, and I could be just overinterpreting because that's what I do. But one of the things that Jean-Luc didn't mention is that part of the microstructure of the cartridges themselves is that they have built-in filters. So you can imagine all the particles flowing through this nanoconstrictions. And one of the problems with the other implementation of this technology is that when a particle that's bigger than the nanoconstriction shows up, it clogs it and you can't make a measurement anymore. The way our system works is we actually have upstream filters that keep the large particles that would clog the nanoconstriction from ever getting there. All right. So I can measure a sample that has 1,500 nanometer particles in it in a smaller size cartridge and still not have the large particles cause a problem. And that's a really key difference in our implementation of resistive pulse sensing.
Yeah, thanks, Lou. That's a good point.
Ladies and gentlemen, we've come to the point where all the questions have been answered. What a great webinar both Jean-Luc and Lou conducted with lots of engagement. Please reach out to them. The slide shows their contact details, and we very much appreciate such a great webinar. Hope everybody has a great day, and we thank you for being a part of today's webinar. Goodbye.
Thank you very much.
Thank you. Goodbye.
Thank you.